All right, we'll get going again. Thank you, Chris. That was a great walkthrough of all of the snow modeling in Geisha. So hopefully y'all are able to step through that on your own, and then you can try out also some of the pros and grounds options that Chuck mentioned in his presentation. If you go back, you can see those options to turn on and off things. They're also, if you have 11.3, they'll be in the job control option that Chris showed you, where you can just click things on and off and edit those CFGI index and K numbers in there. So thank you, Chris. That was great. Now I'll let you, Dr. Pradhan, let you
Okay,
take it away as far as talk about permafrost and soil hydrothermodynamics.
thanks, Aaron. This is Nawa Pradhan, research hydraulic engineer at ORDIC, Coastal and Hydraulics Laboratory. Let me share my screen here. Can you see my
Yep, good to go.
screen? Okay.
You're not in presentation mode, but we can.
Okay.
There it is.
There we go. I'm talking about hydrothermodynamics. It is so-called hydrothermodynamics. The interesting fact is, we'll see later how we have to exchange the information of hydrodynamics towards the thermodynamics, and then the information from the thermodynamics, how we have to incorporate into hydrodynamics so that it's tightly coupled and all the physical processes are interacting in a physical manner. So this is, more complex in the sense as we move towards more realistic and physics-based approach. The beauty of GSSHA model in itself is there are more than one, process definition in the Vedoshes on saturation, unsaturation interaction. There is Green-Amp, a multi-layer Green-Amp, and now we are touching the recharge equation. So far, what has been discussed was on the one layer kind of thermal transmission. So in this presentation, mostly I will show you and talk about the modeling and the simulation aspect. We saw in the theoretical, like real world aspect, how that functions. A lot of those are discussed by Chalk. Let's see how it really happens when we simulate through the modeling. So we have, basically I put this slide on some of the publications here. These are the main folks who contributed in all those processes so far. And the GIPL, which is the thermodynamics part of the modeling, which is a standalone point-based model, we incorporated that. Along with the incorporation with the point-based standalone model, we had a really good collaboration with the team from University of Alaska at Fairbanks. And mostly right now, we really remember Professor Sergei Marchenko, who passed away this year. And, we learned a lot from him and his team. We are always thankful for this collaboration. So permafrost is something like, it's kind of, rocky surface on the bottom that acts kind of rock in the sense, and that's lasting for a long time. But actually in the definition, if the frozen ground exists for 2 years and more, that's called permafrost. Here is one, you can see the scale, how deep it can go and how wide it can extend. And like Chalk mentioned in one of his slides, this incorporates almost 1/5 of the Earth's land surface. That's what we find in literature, So basically, we tend to see those kind of frozen ground, so-called permafrost, in the mountainous I mean, in the higher latitude, or the lower latitude or higher latitude, basically. But sometimes this is not only in the higher latitude, but it can happen in the lower latitude as well. For example, Himalayas, if you consider those area, it's only 26, 27 degree in the latitude of that range towards north. But because of the altitude, it makes a big difference. So there are scattered, discontinuous permafrost existence, and likewise in Mount Kilimanjaro. So it's necessary for us to, model and make a hydrological model anywhere in the globe, in the world. So at times, we may have to deal with permafrost simulation and modeling. So what is the main case here in the hydrological part because of the influence of permafrost is that if there isn't permafrost or there isn't frozen ground, then it acts just normal. So here is the equation. If the temperature is greater than 0, everything is in normal condition, then there is this equation derived in Colorado State University long time back, so-called Brooks and Carney. And this kind of equation actually functions pretty well when we are getting the unsaturated hydraulic conductivity as a function of soil moisture and the saturated hydraulic conductivity. But this doesn't exist when it goes towards the frozen part of the frozen condition, in the frozen condition. Basically, some of those equations Zach already mentioned, which is an exponential function. So as temperatures go down, what actually happens is the void in the soil column, there is air and water, right? So any water that exists in that partially freezes. As the amount of water that's freezes and then free water is lessened, then the hydraulic conductivity exponentially decreases, and at one point it acts like a concrete or the solid rock where there is no infiltration. So this is the real case simulation that we published, done in Alaskan watershed, part of Poker Creek. As you see here, when the air temperature is really low in the freezing condition, the hydraulic conductivity is like almost 0. And then as the temperature goes up, then slowly the hydraulic conductivity comes to the normal condition. But without that, incorporating thermodynamics, what happens here, the hydraulic conductivity just acts as normal. In this case, it makes a big difference in the simulation result, except that if you want to really calibrate and make unrealistically the hydraulic or saturated hydraulic conductivity low. But then again, you fail if you are doing long-term simulation after this point, because there is sudden increase in hydraulic conductivity, right? Therefore, those processes are necessary. Looking at the physical process of the thermodynamics and hydrodynamics, it looks pretty similar here. One is from the recharge equation in GSSHA. Another part is the thermodynamics equation from the Geophysical Institute Permafrost Laboratory, that's GIPL. It's pretty similar, except that one is the mass balance equation in terms of flux in the hydrodynamic part. Another is the energy balance, the heat flux in the temperature part. And interestingly, two equations are significantly governed by one dominating parameter. On the left-hand side, the so-called the hydraulic conductivity. On the right-hand side, so-called thermal conductivity, right? So there is this information exchange is needed when we are considering this hydraulic conductivity and thermal conductivity, because hydraulic conductivity is influenced by the temperature, like we just explained in the previous slides, and thermal conductivity, on the other hand, is significantly dependent upon the soil moisture condition. Actually, thermal conductivity of frozen ground is much higher than the thawed soil surface. So coming back to how we developed the architecture, at that time it was really new concept, and we developed this in this fashion. If you look at these two sides, which are kind of box shaped, one side on the right hand side is for the soil column, right? So what happens in the dynamics of the soil moisture in the soil column is that the soil moisture can go from residual saturation to porosity. That's the maximum extent. And below the capillary head, where it's still called saturated, and then there is the dynamic groundwater table. The water table goes up and down, influencing the soil moisture also. But on the other hand side, in the same soil column, the temperature goes from negative and positive. It swings in this fashion. So what we did interestingly here is that for any location in the soil column from the thermodynamics part to any corresponding location towards the soil column in the thermodynamics part, we exchange this temperature simulated by the hydrodynamic part, and then from the hydrodynamic part, we exchange the soil moisture towards the thermodynamic part. So this exchange of information then internally calculates what is the realistic, the thermal conductivity and hydraulic conductivity, and then henceforth in each time step. Now, how we incorporate the time step, a user can define on their own. Otherwise, it's in the time step of infiltration. The other interesting part here is a user doesn't have to define the segmentation or the computational units of the hydrothermodynamics exactly similar to thermodynamics. Actually, it's much different than one another. But what is similar in the sense how the simulation goes and unstability are taken into account. The first top layer and second layer, the computational units or stratification of these units are finer in both the cases. As we move down deeper into the column, the computational units are wider apart. But in soil temperature part, it can go up to hundreds of meters down. Actually, that's also kind of necessary to get the boundary condition on the geothermal activity part, which is we try to find that which has less gradient overall in the lower surface boundary condition. The initial condition, two of the initial conditions when you are simulating the hydrodynamic and thermodynamic, so-called hydrothermodynamics, are the soil moisture initial condition and the temperature profile. Both, since you are dealing with recharge equation, has to be in the soil profile, right? So I want to touch a little bit on this aspect because we are also doing overall how to incorporate different kind of data and how to derive new techniques and bringing those new methods which is verified then into the hydrological model like GSSHA, which is physics-based, right? So in this case, for the soil moisture, we have the soil moisture that's a function of evaporative fraction and the soil properties, which is basically called SARV's method, which has incorporated the index, vegetation index part, and the soil physical properties here in this equation. So, having said that, the beauty of this equation is actually it gives the root zone soil moisture. And usually when we define the satellite-based soil moisture, it's on the top thin skin of the soil surface, because the reflectivity doesn't penetrate. That's the source from satellite deep down. But this one then gives the soil moisture of the root zone, which is 2 meters maybe for this big tree or more than that. Why it gives better soil moisture, or why it represents the root zone soil moisture, so that can be defined as a profile soil moisture, is that the canopy and the health of the canopy itself is defined by how much moisture exists in the root zone, right? And that's the reason it's kind of inverse relationship due to the canopy existence, or how healthy is the canopy. It defines the soil moisture in the root zone, and that's in the root zone depth. Similarly, there is also temperature. Some data of temperature, like land surface temperature, and also you can get the reanalysis data, but these are in coarse resolution so far. And if there is good way to downscale those, we are coming towards more physically realistic initial conditions. I'm talking about this initial condition in hydrological model like GSSHA. Initial condition plays a most important part. It's just like you're dealing with really dominant parameter like hydraulic conductivity. Although initial condition is not the parameter, it's a state, and it cannot be treated as parameter, right? So. And most of these simulations are from Caribou Poker Creek, here shown in the left-hand side of this slide. So as we simulate here, the temperature based on the air temperature, how that influence the deeper down soil profile temperature. You can see here how it is verified, right? At 10 centimeter deep, you have the temperature going from below 0 towards higher temperature along the time. If you go towards the deeper soil profile, it doesn't vary like here shown on the top graph. It is more like consistent and constant throughout the time. That is what I was talking about. The deeper temperature are more influenced rather than the surface air temperature. They are influenced by the geothermal activities and geothermal temperature down there. So in the freezing and thawing cycles, like seasonal freezing and thawing, how that goes back and forth, you can see on the left-hand side heading towards freezing condition, right, as temperature decrease down, and towards right-hand side, the temperature heading towards the thawing side. And you can see how the soil temperature in the profile goes, or how that is dynamic in nature. If you look at this long-term simulation, this is almost a year of simulation. So when there is the air temperature really negative or low, then that is highly influenced when the soil column is on the top surface or very close to the surface. And you can see the lag time isn't that much, but as you go deeper down in the soil column, there is a longer lag time, and as you go even deeper, like 5 meter and so forth. It is hardly influenced by the air temperature. So this is one of the case how the air temperature and the initial condition, defines the soil column temperature. I think this is the beauty of using more robust physics-based hydrothermodynamics, numerical simulation, and we can get inside of a lot of things, how things are going, right? For example, if there is fire, then that can hint through the simulation, provided we have how much temperature is on the surface, that could influence how deep down into the soil column, whether it's there is a frozen ground or if there is a permafrost. Actually, these equations that I'm showing is not only confined to frozen ground and permafrost. It can be in the normal condition, in a very high temperature, it can be equally good. So here are some results and analysis. This is one of the graph I showed in the previous slide. And here you can see another one. As if the hydraulic conductivity goes really low, then what happens? The infiltration is low, and the surface runoff is really high. So it has a consequential effect. So we can see all cause and effect relationship in this, as we develop this process and get into the simulation, rather than just turn the knobs and use the degree of freedom and calibrate and get the answer. So you can see all these state like infiltration at a point, at time, discharge, and other parametric values, how that are changing in the time. So as far as setting of thermodynamics model, we have Chris, who is going to demonstrate a tutorial on that. And it is developed in WMS as a WMS tutorial. There is an example, but the basic guidelines are published on the right-hand side. So you can go through those guidelines. That has informations of theory, and also any reference for other theories is incorporated in that. So there are a whole lot of inputs and outputs. We will deal with that in the tutorial side, and different parameters that is incorporated are in this table 6. Actually, this is the table 6 of that report. So, and the report does have what is the parametric value range for different conditions. And here, as we go through the tutorials, there are different, files that you have to incorporate. Some are input files, and one of the main input file, as you use WMS produce all these input files for GSSHA, but usually you have to know that these input files are governed by keywords or so-called card. So if you are using thermodynamics, which incorporates GIPL in the recharge-based simulation, then you apply permafrost _ GIPL. That's the main card. Then the model then knows, hey, we are simulating now permafrost. Now, where is permafrost boundary? Now, this boundary is something like you have to tell which is the area that you want to simulate. This is for if a user understands or knows to some extent where the permafrost exists, right? Right now, we are also working on those kind of initial estimation or probability of frozen ground and permafrost from machine learning. So it has been published. Please contact us if there is any interest in that front. And there are other cards, which is out under GIPL underscore temperature. That card signifies what is your output file. So all the outputs of actually is the temperature profile at different depths are defined in this file. And here there are other input cards where you have to define what is the computational node for the soil profile. So for soil type 1, permafrost soil type 1, and it could go on for soil type 2 and 3, you know. And these are defined by WMS. When you are just developing the model or a standalone GSHA model you are using without WMS, it can be a little bit more tedious, but WMS simplifies everything so much. An initial temperature for each soil type, you have to define that, which is in WMS, the facility for that. And then there, finally, you are looking for what are the output nodes, output locations. So there you define which places you are interested to get output as a soil temperature profile. So there was earlier questions about where we can get the water depth, whether we can get that in overland as function of time. And exactly, you can get the soil temperature, actually not only one place, but these are like output location, you know, XY. 6 means row and column, 6 row, 6 column. And then you want to get the output at 0.1 depth, 1.5 meter depth, 5 meter depth, or whatever meter you are interested in. And the output would be something like time series on the left and the corresponding air temperature, and then there is depth of 0.1 and then temperature at 0.1 and so forth. 1.5 meter temperature at 1.5 meter and so forth. So I guess that's it. Thank you. If you have any questions, reach out to this team as well to me. Thank you. Any questions?
And one question.
Yep. That's internal. Go ahead, Aaron.
What depth of soil root zone moisture does GSSHA model simulate?
What's that? What depth?
What depth of soil root zone moisture does the GSSHA model simulate?
Actually, it depends upon you who are using GSSHA, right? You have to define the soil moisture depth. So that's the root zone, which is explicit. I'll write that in the wiki at one point. I think that's necessary. We got to incorporate. So actually in the evapotranspiration, any moisture that's extracted out from any grid soil column, it doesn't happen in throughout the column of unsaturated zone. It just happens in the root zone depth. That's the soil moisture root zone, right? So that is one thing. And the beauty of getting the root zone soil moisture as an example defined, I already showed as SARS method, would be really significant, especially in arid and semi-arid region where this method has been verified. Any questions?
That's it for now.
Thank you.
Permafrost map table ID. So I'm going to enter 1 here, and I need to do that with this this other point also. So I'm going to put 1 there for the permafrost map table ID. And that, oh, actually this other one, I do a map table ID of 2.
Yeah.
So they have to be different map table IDs. Then what I can do is go ahead and save my model and run it. So I've defined my outputs, I've defined my mapping tables, defined everything I need to do permafrost. And we're going to save this. Go to the 2D grid module. We can save this project. And we're going to go here to demo. And then we can go ahead and run it. Run GSHA. And just use the defaults here. It's going to run through this. It's a short long-term simulation. Won't take a long time to run. It's also kind of a lot smaller model. So it takes a few seconds to run, and then it has this option to read the solution on exit. And okay. So when I read the solution, there's a couple of outputs here. Now the hydrograph, has these little hydrograph icons that seem to be messed up, but if I click on these, if I just double click on one of these, it brings up this plot. And what this plot shows is at that point, I had GSSHA compute the temperature at different depths in my model.
Yeah.
At each time, at different times. Okay, and so that's what this plot is. This plot showing, I guess, like the pink, or actually the black. There's a black line in here somewhere that shows. Oh, that's just this line here that goes the most variable line. That's just the air temperature.
Air temperature.
And then
so let's see from this is exactly what the earlier simulation that we had. The similar kind of output we are getting. The influence of air temperature is having much on the surface that's very close to the surface of the Earth, right? Towards, as you go deeper down in the soil profile, then the influence of air temperature isn't much. As you see the pink, which is 3 meters. But again, this is like you put the thermal conductivity, and if you play around I think it's good to do the sensitivity analysis of the parameter here. So as we change the thermal conductivity, that may change all these output results accordingly, but in a meaningful way. So thank you, Chris.
yeah, no problem. And then the other thing you might want to look at, so here's the other one. You can look at the same plot, a similar plot on the other output node I've defined. And then the other thing you're going to get is a hydrograph, which this is the hydrograph for that model.
Yeah, what I would say is there is another baseline model. So if you just run that baseline model and see the difference in hydrograph, which I have tried, Chris and myself, we have tried. The simulation result from the permafrost, the hydrograph tends to be bigger. So at least the peak.
So you're just saying if we turn off permafrost.
Yeah, but
and then
let's
maybe if we
remember
save,
what peak here, the peak value.
Save a new project file called baseline.prj. Actually, let me just, what we can do, I guess, is we could say, let's turn permafrost back on. I can duplicate this model, and we'll make another model called baseline. And I'm going to save that project file out. And I guess the difference is, so I need to go to the job control here. Job control and turn off permafrost. And then we'll just try running that, save it. Read the solution. Not sure why that error message comes up, but we can look at the output hydrograph. Outlet hydrograph for the permafrost model is here. And then the outlet hydrograph for the baseline is there. So there's some difference, I guess, in those output hydrographs. But just have to think about that, about why they're different.
Yeah. Is this the groundwater, GW.PRZ?
There is, yeah, so there, it is running groundwater. So if I look at this, wait, maybe it's not. I might have turned that off.
Yeah.
Let's go to
You
job.
started this
Yeah, I
at
turned off the
base
groundwater. We don't.
Ground GW. There was this GW.PRZ.
We don't run the groundwater on this, but
Anyways, we can try that later, or let's keep it as, you know, the training process and see what would be the difference between with the permafrost included and without. And that would be another thing. One output we can see instantly from the simulation is the hydrological hydrograph difference in that part. The next thing is the temperature profile, as you are looking for different point of interest.
right. So that's pretty much the end of the tutorial, I think.
Yeah, for this part, yes.
For the permafrost tutorial. Trying to see if there's anything else I should mention. Oh, the other thing you might want to look at is you can go through the summary file. If you just double click on the summary file, it brings that up in a text editor. And does it have anything about permafrost in the summary file?
It incorporates all the balance within that big framework, but actually it doesn't outline individual permafrost, some part, you know, how much less or more.
Yeah, so it has the mass balance there, but
yeah.
Anyway, that's the summary file, all the output. That's it. That's pretty much it for the tutorial. Aaron, you still there? Noah, did you have anything you wanted to add?
Talk.
No, that's good. Thank you, guys. Thank you. Thank you. So I'm working on upgrading the Judy's branch model from the snow routine to add the Richards infiltration and then add the permafrost. It takes a lot longer to run, so
yeah.
But when those are done, I'll put them up on the website as well, so y'all are able to walk through those as well. So, thank you. Any comments or thoughts or questions about permafrost in GSSHA? Looks like we're doing pretty good then. Everybody was like on top of it. So good job. Well done. So again, like Chris showed you, those websites, the tutorial models are on the GSSHA wiki. Rosie has a question. Can we get a GSSHA wiki tutorial on the temperature index snowmelt method? Most use-case districts that are interested in snowmelt have access to near continuous SWE data from NRCS SNOWTEL sites, so would be able to calibrate the TI method. The only GSSHA wiki tutorial is on the EB snowmelt method. Yeah, that'd be something we can put together. That would be great.
I mean, it's pretty easy to change between the methods. There's not there's not that many factors you have to set. But I don't guess there's an actual tutorial like you're saying. But all of the different factors are explained on the wiki. And so if you were to get that tutorial for one method and kind of look at the wiki, I think you'd be able to kind of figure out what to play with, like you're saying.
So, Chuck, looking at
Yeah.
the temperature index method, we were using the default is this hybrid energy balance method, right?
Yeah.
And the temperature index method has these two parameters.
It has 9 parameters.
So it has all this stuff.
Yeah. The hybrid one is in my opinion better than the TI. But that's not, I guess in the wiki it's only got, you're saying only the energy balance. Yeah, I think that, I mean, I would suggest the hybrid personally. It's in the WMS as well, Chris, or no?
The hybrid?
Yeah, what do you
The
got in
hybrid
there?
is just the default.
But there's 4 parameters it said in that presentation. And I don't remember what they are. It's been a while
Well,
since
it
I've
had
used snow
the
modeling.
yeah, I don't know, but it had in the tutorial it had you enter the dry adiabatic lapse rate and the elevation of the gauge, just so you can get the change in elevation, I guess.
Right, yeah.
And then
We get to change the temperature with elevation.
and there was some other parameter that we entered in the tutorial. I can't remember which one it was, but you can. I think some of them are optional. There's some default. Oh, it was this base temperature to begin melt. We change it to 5.
Yeah.
And but I guess you could leave those at the default too. But you probably, like, if you're in a mountainous area, you obviously wouldn't want it. You'd want this dry adiabatic lapse rate defined and the elevation.
Well, you can use a moist adiabatic lapse rate too. So there's a few options on how you do that.
But you can't. Can you do that with just a separate card, different card?
Yeah.
But I guess we don't support that in WMS.
Yeah, I don't recall using the moist adiabatic lapse rate in an actual project personally. But it is in there. And it's all in the wiki. It describes every single parameter and every single card that you'd have to put in your project file, whether or not it's in the WMS or not. So probably the best way to.
So what if you have a snow water equivalent map? How does that work? If I have a map,
That's like an initial condition. Like you
Yeah.
might want to start in January or something, and you have measured values, then you could put them in there and start from them.
Okay.
But if you start like we did in October and let the model initialize itself, then you don't have to do that.
Mhm.
Yeah, I see. So is the only other required parameter for the temperature index, the maximum melt factor and the minimum melt factor, which I guess they have these default values.
There's 9 parameters. I can't. That's so small.
We didn't do it. Did we not do the interface right? For the temperature
You might have just
index?
you might have just had it. It might just write out default values, and maybe it might be that you don't calibrate all those values. You just calibrate a couple of them. I've never used the temperature index method. I've either used. I wrote the energy balance a long time ago. And that's what I used until Mike came with a hybrid. Then I started using it because he said it was the best one. So.
Okay.
So they might not all be exposed, at least, and maybe WMS writes default ones.
Yeah.
I don't know because I don't have a lot of experience actually setting up the models for those.
Okay. Yeah, you can play around with it.
as Rosie's pointing out, the GSSHA snowmelt tutorial talks about the TI model is the most accurate when calibration data in the form of SWE is available. So,
Yeah, I think the problem is the data.
Yeah, usually if there is initial condition which is more realistic, the outputs are much more, better.
yeah, so we'll work on that, Rosie. Thanks for the feedback. We'll work on a temperature index tutorial. Great feedback.
Yeah, we could do that next year. Some of the H&H set funds.
Yeah.
And it's just be adding to that one tutorial, really. We'll be making a new one.
Great question. Other questions? We're wrapping up a little early here, so. All right, if nobody's jumping in there. Well, thank you, everyone. We'll wrap up a little early here then. I hope you've learned a few things about how we can simulate cold regions, different options that are available in watershed modeling system and in GSSHA for adding the different processes, and a bit about how the different processes actually play a role in the hydrology of cold regions.
And Aaron, you're going to mail out them. You get 4 hours of whatever in the world they're called.
PDH hours, yes.
Contact hours.
Contact hours.
If you're a PE or something like that, then you can use this. We're official trainers, Aaron and I, at least.
Yes. So I'll send those out later on this week. I believe I have everybody's emails, so we should be good to go. So, if there's any last questions? Here's one from Sunil. How challenging is it to use this model in data scarce regions, and what strategies can be employed to effectively utilize it in those areas?
Satellite-based data.
Yeah.
That's the option. So we are working on that part, get most of that, especially the initial conditions and things like that. Gene is here. He's working on soil with us, or especially with me past 1 year or so. We're trying to get the worldwide data of, soil type and textures and incorporate that in terms of, conductivity, both the thermal, hydro, and all these falls into literature, pulling back the inverse relationship or pedo transfer, right? So that's one of the things, just an example. But for example, soil moisture, which is really hard, but with the advancement of the technology and the satellite information like vegetation, it gives some information. Likewise, there is also data of, snow water equivalent or content through, at least from MODIS imagery and things like that, which goes like pretty frequent. How we track that and put it as an initial condition, that makes a big difference as well. And these are also the temperature, right? So satellite-based data are the solution for ungauged basin. That's why our, GSSHA model is the future of, modeling any place in the world. One thing is it's physics-based. It can relate to the physical properties as it is stressed by land use, soil types, and things like that. So the earlier concept of, well, it is physics-based, it has a lot of parameters. That concept is now, I think it's reversing in the sense that a physics-based model could be a solution for ungauged basin. as you can transfer those kind of similarity properties in place.